Close your eyes for a moment and imagine yourself drifting back in time. Not thousands of years, not even millions, but billions. 2 billion years ago, Earth was a planet both familiar and utterly alien. The continents were there, but not as we know them. The oceans stretched wide, but they were not the same shimmering blue seas we see today. The skies, too, were different, less rich in oxygen, more tinted with gases that would feel harsh and unbreathable to us now. And life, it was present, but life as simple as can be, made of single-celled organisms that had already begun to alter the very face of the planet. 2 billion years ago, the Earth was in transition. The Great Oxidation event, which had begun hundreds of millions of years earlier, had raised oxygen levels in the atmosphere for the very first time. It was a revolution invisible to the eye but monumental in its impact. Oxygen, once scarce, had begun to accumulate, slowly changing the chemistry of oceans, rocks, and skies. Yet the air was still far too thin in oxygen for animals or plants as we know them. The planet was caught in a delicate balance, not yet ready for complexity, but no longer the same as before. If you were to stand on the land, though in truth, most of Earth's surface was ocean, you would find a barren world. There were no forests, no grass, not even moss. The continents were rocky, with perhaps thin soils just beginning to form in sheltered places. Wind swept across wide plains of stone, while rivers cut through primitive landscapes. The continents themselves were grouped together in supercontinents, massive landmasses that broke and collided over time, reshaping the surface slowly but powerfully. The oceans, too, told a different story. They were rich in dissolved minerals, often greenish or reddish in color because of iron and other elements. The waters may have looked cloudy or murky compared to our modern clear blue seas. Yet within those ancient waters, life was everywhere, tiny, microscopic, invisible to the naked eye. Cyanobacteria, the small architects of oxygen, floated in mats and colonies, slowly exhaling oxygen with every breath of sunlight. Their work was steady and patient, transforming the world in ways that would only be seen much later. Above all, Earth 2 billion years ago was a world of patience. The dramatic events of the planet's early youth, the bombardments, the fiery seas of lava, the first atmosphere thick with methane and carbon dioxide, had passed. The grand bursts of complex life that would fill the Cambrian seas were still unimaginably far in the future. Instead, Earth existed in a kind of balance, a long chapter of subtle changes and quiet preparation. To us, it may seem uneventful, but this balance was crucial. Without it, life could not have continued to evolve. Oxygen had risen but then stalled at low levels, creating what scientists sometimes call an oxygen plateau. Nutrients were limited, meaning life expanded slowly, step by careful step. Yet in this quiet, hidden progress was happening. Somewhere in the oceans, cells were experimenting with new forms, preparing the way for more complex structures. The eukaryotes, the ancestors of all plants and animals, were beginning to appear, although they were still rare and fragile. In this series, we will walk through that ancient world together. We will explore its oceans, its skies, its continents, and its life. We will look at how scientists have uncovered its secrets, reading clues written in ancient rocks and minerals. We will see why this time, though often overlooked, is one of the most important chapters in Earth's story. Imagine, then, a planet under a softer sun. The sunlight was dimmer than today, the days shorter, the moon closer in the sky. The tides were stronger, pulling on oceans with more force. Storms rolled across the seas, rains fell on rocky lands, and glaciers may have formed in cooler intervals. It was a dynamic Earth, yet also a restrained one, holding steady for millions upon millions of years. As you listen, let yourself sink into the calm of this ancient time. The rushing noise of modern life fades away, replaced by the steady rhythm of waves against stone, the slow drifting of continents, the silent work of microbes in the sea. This was Earth 2 billion years ago, quiet, patient, alive in ways almost invisible, yet laying the foundations for everything that would come. In the chapters that follow, we will journey deeper into this forgotten world. We will see how its climate, atmosphere, and geology shaped life, and how life in turn shaped the planet. We will explore why Earth did not remain in this state forever, and how from this balance, change eventually erupted. For now, though, picture that ancient Earth in your mind. A world without trees, without animals, without flowers or grass. A world of stone and sea, sky and storm, with tiny forms of life floating unseen in the waters. It is a world both alien and familiar, for though we could not survive in it, it is still our home, our planet, our shared past, and in its quiet depths it was preparing for us. 2 billion years ago, Earth was still adjusting to one of the most profound changes in its history, the rise of oxygen. Before this transformation, the atmosphere had been almost entirely devoid of free oxygen, dominated instead by gases like methane, carbon dioxide, and nitrogen. But a quiet revolution was already underway, driven not by volcanoes or asteroids, but by tiny organisms floating in the oceans. These were cyanobacteria, often called blue-green algae, though they are not algae at all. Through the process of photosynthesis, they harnessed sunlight, water, and carbon dioxide to produce food, and in the process, they released oxygen as a byproduct. This steady release of oxygen, happening on scales of millions of years, slowly altered the composition of the air and oceans. Scientists call this great transformation the Great Oxidation event. By the time we reached 2 billion years ago, the Great Oxidation was no longer new. It had begun hundreds of millions of years earlier, around 2.4 billion years ago, and its first dramatic impacts had already played out. Methane in the atmosphere had reacted with the new oxygen, collapsing the methane greenhouse and plunging Earth into some of its earliest ice ages. Iron dissolved in oceans had rusted, falling to the seafloor and leaving behind thick layers of banded iron formations. Geological records still visible today. By 2 billion years ago, oxygen levels had risen above zero, but had not yet reached anything close to modern levels. Estimates suggest that the atmosphere contained only about 1 to 2% oxygen at this time, compared to the 21% we breathe today. For us, it would have been a suffocating world. But for life then, it was transformative. Oxygen allowed new forms of chemistry, enabling organisms to generate far more energy from food. It also changed the environment, altering minerals, rocks, and the cycling of elements. The transition was not smooth. As oxygen spread, it poisoned many organisms adapted to an oxygen-free world. Microbes that thrived in methane or sulfur-rich environments were forced into isolated habitats, deep sediments, hydrothermal vents, or oxygen-free pockets in the oceans. For them, oxygen was toxic. But for others, oxygen was an opportunity. This delicate balance, a mix of survival and extinction, defined the world of 2 billion years ago. The oceans reflected this transformation as well. In shallow waters, near sunlight, oxygen accumulated, supporting photosynthetic microbes and early eukaryotic cells. Deeper down, however, the oceans were still anoxic, meaning oxygen poor, and often rich in dissolved iron and sulfur. These stratified oceans created sharp boundaries, with very different chemical worlds stacked on top of one another. For life, it meant niches. Different microbes adapted to each layer, from oxygen users near the surface to sulfur-breathing microbes in the depths. Geologically, the world was responding too. New minerals formed that had never existed before the rise of oxygen. Rocks were oxidized, landscapes were reshaped, and the chemistry of rivers and soils changed. This was the beginning of a more dynamic interaction between life and geology, where biology no longer simply survived on the planet but began to shape it. The evidence lies in the rocks. Red beds, sediments stained with iron oxides, began to appear, a sign that oxygen was present in the environment. These silent witnesses still remain in cliffs and outcrops around the world, whispering the story of transition. 2 billion years ago, Earth was no longer the alien planet of its earliest days, shrouded in haze and dominated by methane, but it was not yet the breathable, green world we know now. It was a planet between states. Oxygen had risen, but then it plateaued, stabilizing at low levels for nearly 1 billion years to come. This period of stability, neither too low nor too high, became the stage for what scientists later nicknamed the boring billion. But to call it boring is misleading. This was 1 billion years of balance, of waiting, of subtle preparation. Oxygen remained low, but stable enough to support innovation. Life was still microbial, but within those cells important experiments were taking place. The first eukaryotes, cells with nuclei, emerged during this time. The Great Oxidation had not only reshaped the environment, it had reshaped the possibilities of life itself. As you imagine this world, think of a planet holding its breath. The skies carried a faint trace of oxygen, enough to change chemistry but not enough to support animals. The seas were layered greenish or reddish from dissolved minerals. On the rocky shores, microbial mats clung to the edges, quietly pumping oxygen into the air. It was a world not of silence, but of patience. The Great Oxidation had set the stage, and now Earth was adjusting, waiting for the next leap forward. The story of 2 billion years ago is a story of transition. Not yet the lush world we know, but no longer the alien sphere it once was. The Great Oxidation event was not a moment, but a long unfolding. And 2 billion years ago, Earth was in the midst of that transformation. In the next chapter, we will explore what the atmosphere itself was like during this time. Thin, oxygen poor, but uniquely stable. It shaped everything about life and climate on the ancient Earth. 2 billion years ago, the atmosphere of Earth was unlike anything we know today. To breathe it would have been impossible for us. Oxygen was too scarce, carbon dioxide levels were shifting, and methane, once dominant, had mostly disappeared. Yet this alien air was the foundation on which modern Earth would eventually be built. It was an atmosphere in transition, caught between the old world of anoxic chemistry and the new world of oxygen. To understand it, imagine standing on Earth's surface at that time. The sky above would not have been the brilliant blue we are familiar with. Instead, it may have appeared hazy, tinted by gases and particles. Clouds would still have formed, storms still would have rolled across the land, but the balance of gases that colored the sky and fed the oceans was different. At the heart of this difference was oxygen. Today, oxygen makes up about 21% of our atmosphere. 2 billion years ago, however, it was closer to 1 or 2%, perhaps even less in many places. That may sound like almost nothing, but it was a monumental leap compared to earlier times, when free oxygen was virtually non-existent. The Great Oxidation event had introduced oxygen to the air, but its rise had slowed. For hundreds of millions of years afterward, levels remained low, never reaching the richness that animals would one day require. Why did oxygen plateau? The answer lies in balance. Oxygen was being produced by cyanobacteria in the oceans, but it was also being consumed by reactions with rocks, minerals, and volcanic gases. When oxygen met reduced iron or sulfur, it reacted, vanishing from the air. The Earth itself was a sponge, soaking up the new oxygen. Only once these sinks filled up could oxygen accumulate further, but around 2 billion years ago, the balance had settled into a long stability. Carbon dioxide, another critical gas, was also present in much higher amounts than today. Volcanoes released it constantly, and without abundant plants to consume it, levels remained elevated. This greenhouse gas helped keep the planet warm under a sun that was dimmer than it is now. Without it, Earth might have frozen completely. Instead, the balance of gases maintained climates that, while different from ours, were still habitable for microbial life. Methane, once a dominant gas before the rise of oxygen, had nearly vanished. Oxygen reacts quickly with methane, breaking it down into carbon dioxide and water. This loss of methane changed the greenhouse balance dramatically. In earlier eons, methane had helped keep Earth warm, but once oxygen spread, that source of warmth declined. This may have contributed to episodes of global cooling, including ice ages. 2 billion years ago, the planet was recovering from such shifts, finding a new equilibrium in its atmosphere. Nitrogen, the most abundant gas today, was already a major player 2 billion years ago. It likely made up the majority of the air even then, just as it does now. Inert and stable, nitrogen provided the background against which oxygen and carbon dioxide fluctuated. Together, these gases created a composition that was stable enough to endure for nearly 1 billion years, with only small changes over long stretches of time. This stability is one of the most striking features of the atmosphere at the time. For about 1 billion years, from roughly 1.8 to 0.8 billion years ago, oxygen levels remained low but steady, carbon dioxide high but balanced, and the climate relatively moderate. Scientists sometimes call this period a boring billion, because, compared to the dramatic swings of earlier or later ages, little seemed to change. Yet in truth, this stability was extraordinary. It created a consistent environment in which life could experiment, evolve, and slowly prepare for future leaps. The atmosphere was not just a passive backdrop, it shaped the oceans, which in turn shaped life. With low oxygen, the deeper oceans remained anoxic, filled with dissolved iron and sulfur. The surface layers in contact with the air carried oxygen, but only in thin bands. This stratification created worlds within worlds, oxygen-rich shallows above oxygen-poor depths. The thinness of oxygen in the air meant that it penetrated only so far into the seas, leaving much of the planet's water chemistry alien to us. Even the color of the sky might have been different. With less ozone in the upper atmosphere, ultraviolet light from the sun would have been harsher, scattering differently than today. Some models suggest skies may have been paler, perhaps even tinged with subtle hues. For early microbes, this radiation was dangerous, but it also provided energy for chemistry. Life adapted by clinging to water, rocks, and mats that shielded it from the harshest rays. One of the most fascinating aspects of Earth's atmosphere 2 billion years ago is how it influenced the long-term trajectory of the planet. By holding oxygen levels low but steady, it delayed the rise of animals, which require much higher concentrations to survive. At the same time, it allowed eukaryotic cells, the ancestors of all plants and animals, to begin their slow evolution. The air of this era was both a barrier and a bridge too thin in oxygen for complex creatures, yet stable enough for complexity to quietly take root. Geological records support this picture. Layers of red-stained rocks, formed by oxidized iron, show that oxygen was present, at least in surface environments. But the continued appearance of certain sulfur isotopes, which only form in low oxygen conditions, shows that oxygen never fully dominated. The Earth of 2 billion years ago was in between, caught in a balance we can read today in stone. As you imagine this ancient atmosphere, think of a sky hazy with gases, thin in oxygen, thick with carbon dioxide, and perhaps harsher in sunlight than today. Imagine breathing air that would suffocate us in minutes, yet supported life perfectly suited to it. Picture storms rolling across barren continents, carrying rains that dissolved new minerals, feeding rivers that ran to seas layered with oxygen, rich surfaces, and anoxic depths. It was not our world, but it was stable, balanced, and enduring. For nearly 1 billion years, this atmosphere sustained Earth, quietly preparing the way for future revolutions. In the next chapter, we will descend from the skies into the oceans themselves, exploring what seas looked like 2 billion years ago. Strange, layered waters where microbes reigned and chemistry held secrets that shaped the future of life. If the atmosphere of 2 billion years ago was thin in oxygen, the oceans were even more alien. They were not the clear blue waters we know today, teeming with fish and coral. Instead, they were strange, layered, and chemically complex. To plunge into those seas would have been to enter a world dominated not by animals, but by microbes. Bacteria and archaea that ruled the waves in ways we can scarcely imagine. Picture standing on the shore of a continent still barren of plants. No grasses grew along the beaches, no forests stretched inland. Instead, bare rock met the water. The seas may have appeared darker, tinted green or even reddish-brown, depending on their chemistry. This was not the sparkling blue of modern Earth, but waters infused with dissolved minerals, gases, and microbial blooms. At the surface, in shallow zones where sunlight penetrated, oxygen was present. Cyanobacteria floated in mats or filaments, using photosynthesis to capture sunlight and release oxygen. These thin surface waters were oases of oxygenation, islands of breathable chemistry above a vast, oxygen-starved abyss. The oxygen did not penetrate deeply. Just a few tens of meters below the surface, conditions changed dramatically. Deeper down, the seas turned anoxic, completely lacking free oxygen. Instead, they were rich in dissolved iron and sulfur. When oxygen from above mixed downward, it reacted with these elements, producing chemical gradients that microbes exploited. Some bacteria thrive by using iron instead of oxygen, precipitating it out of the water as minerals. Others used sulfur, producing hydrogen sulfide gas that gave parts of the oceans a noxious, rotten, egg smell. These chemical reactions left their mark in rocks, preserved for billions of years. One of the most striking features of these oceans was their layering. Scientists call them stratified oceans, meaning that the surface and the depths were separated chemically and biologically. At the top were oxygenic photosynthesizers, cyanobacteria and early eukaryotes. Beneath them lived communities of microbes that could not tolerate oxygen, instead using sulfur or other compounds to survive. Still deeper, near hydrothermal vents, archaea thrived on the chemical energy released from Earth's interior. Each layer was a world unto itself, with limited mixing between them. The chemistry of these oceans was dynamic. Iron played a central role. In the absence of oxygen, iron dissolved easily in seawater, turning the oceans into vast reservoirs of metal. When oxygen entered, it reacted with the iron, forming rust-like minerals that settled to the seafloor. Over time, these processes created massive deposits of banded iron formations, alternating layers of iron, rich rock, and silica. Today, these formations are mined for steel, but in their origin, they were records of an ancient dance between oxygen and anoxia, surface and depth, life and chemistry. Sulfur was equally important. Microbes that used sulfur compounds produced distinctive chemical signatures preserved in rocks. These isotopic fingerprints reveal that large parts of the oceans remained anoxic for hundreds of millions of years after oxygen appeared in the air. In fact, scientists believe that hydrogen sulfide may have accumulated in some mid-depth waters, creating toxic zones inhospitable to most life. Such conditions may have suppressed the rise of complex organisms, locking Earth into a microbial world. Despite this alien chemistry, the oceans were alive with activity. Microbial mats flourished in shallow waters, binding sediments and creating stromatolites, layered structures that can still be found today in places like Shark Bay, Australia. These stromatolites were ecosystems, with cyanobacteria at the top capturing sunlight and other microbes beneath recycling nutrients. Each mat was a miniature world, resilient and enduring, shaping the flow of carbon, nitrogen, and sulfur through the seas. The oceans also hosted early eukaryotes, cells more complex than bacteria, with internal structures like nuclei and mitochondria. Though still microscopic, these organisms represented a profound leap in evolution. They likely competed with and sometimes consumed bacteria, experimenting with new strategies for survival. The partnership between cells that would eventually give rise to plants and animals may have begun here, in the layered oceans of 2 billion years ago. The color of these seas would have reflected their chemistry and biology. Green waters rich in cyanobacteria, red or brown waters stained by iron, or even purple hues where sulfur bacteria thrived. Sunlight filtering through such waters would have created eerie, otherworldly effects. To an observer, the oceans would have seemed alien, strange, and unwelcoming, yet within them lay the seeds of future complexity. Currents and tides still moved, driven by the pull of the moon and the heat of the sun. Waves still broke on rocky shores, storms still churned the seas. But beneath the familiar motions, the chemistry and biology were radically different. The oceans were laboratories, conducting experiments in survival and interaction that would shape the future of life. Geological records preserve this story. Banded iron formations tell us about the oscillations of oxygen. Shales and carbonates reveal the cycling of carbon and sulfur. Microfossils of stromatolites and early eukaryotes offer glimpses of the organisms that thrived. Together, these clues allow scientists to reconstruct the strange but vibrant seas of 2 billion years ago. As you imagine these oceans, think of a world without fish, corals, or whales. Instead, life was microbial, invisible to the naked eye, yet profoundly active. Chemistry ruled the depths, with microbes as its interpreters. The surface shimmered with cyanobacterial blooms, while the bottom churned with sulfur, loving bacteria. Between them stretched layers of strange waters, each with its own inhabitants and processes. It may not have been a world we would recognize as alive, yet it was teeming with activity. Every drop of water was filled with microbes, every gradient of chemistry exploited by life. The oceans of 2 billion years ago were not boring. They were alien ecosystems rich in potential, slowly building the foundations for the explosion of diversity that would come much later. In the next chapter, we will leave the waters behind and turn to the continents of the time, lands that looked barren, lifeless and quiet, yet were being reshaped by tectonics erosion and the subtle influences of microbial life at their edges. 2 billion years ago, the continents of Earth were already ancient, but they looked nothing like the landscapes we know today. The surface of the planet was harsh and barren, with no forests, grasses, or flowering plants to soften the land. Instead, rocky outcrops, vast plains of bare stone, and scattered microbial mats dominated the scene. If you could stand on one of these continents, the silence would be profound. No birds, no insects, no rustling leaves, only the wind and the sound of waves crashing against rocky shores. At this time, Earth's landmasses were in the midst of a grand tectonic story. Plate tectonics, the movement of Earth's crustal plates, had already been operating for billions of years. Continents collided and rifted apart, mountains rose and eroded, and supercontinents formed and broke apart. Around 2 billion years ago, one such landmass known as das Columbias, sometimes called Nuna, was taking shape. This may have been the planet's first true supercontinent, a vast gathering of land covering much of the globe. Columbia stretched across thousands of kilometers, linking what are now parts of North America, South America, India, Australia, and Eurasia. Unlike modern continents covered in soil and vegetation, Columbia was stark and exposed. Weathering processes still acted on its rocks, rain fell, rivers flowed, and winds eroded cliffs, but the lack of plants meant there was little soil. Instead, bare rock met the elements directly, and erosion carved the land more slowly. Dust storms carried fine particles, but no grasses held them in place. The colors of the continents would have been different too. Without greenery, the dominant hues were grays, browns, and reds, depending on the minerals in the rocks. Along shorelines, microbial mats may have spread, forming slimy carpets that trapped sediments and created shallow reefs. These mats were likely the only vegetation to be found, thin films of cyanobacteria clinging to wet surfaces. To an observer, these mats might have appeared dark green, black, or even purplish. Depending on the organisms present, volcanic activity was also widespread. The interior of Colombia may have hosted massive volcanic provinces, releasing gases into the air and lava across the land. These eruptions contributed carbon dioxide to the atmosphere, maintaining the greenhouse effect necessary to keep Earth warm under a dimmer sun. Volcanic ash spread across the continents, altering landscapes and feeding nutrients to rivers and seas. In many ways, volcanoes were among the most dynamic sculptors of the land. Mountain ranges rose where continents collided. These ranges were stark, jagged, and raw, lacking the softening effects of vegetation. Erosion still acted, but without roots to stabilize slopes, landslides may have been common. Over time, rivers carved valleys, transporting sediments to the sea. These sediments recorded the story of the continents, clues that geologists study today to reconstruct Columbia's existence. The climate of the continents was also unique. With higher carbon dioxide levels in the air, temperatures may have been warmer overall, though ice ages punctuated the timeline. Deserts likely existed, broad stretches of dry land where winds whipped across barren plains. Rivers and lakes formed in low areas, but they lacked the ecosystems we associate with such environments today. No fish swam in rivers, no insects buzzed above lakes, only microbial life, clinging to surfaces or floating invisibly in the water. Despite their barren appearance, the continents were not lifeless. Microbes colonized cracks in rocks, forming biofilms that extracted nutrients. In hot springs and hydrothermal systems, microbial communities thrived, creating colorful mats similar to those found today in places like Yellowstone. These microscopic pioneers began to alter the land chemically, breaking down minerals and releasing elements back into the environment. Though small, their activities set the stage for future soils and ecosystems. The interaction between continents and oceans was crucial. Rivers carried weathered minerals into the seas, feeding nutrients like phosphorus and iron. These nutrients fueled microbial growth in coastal waters, linking land and sea in an early nutrient cycle. In turn, microbial mats along shorelines trapped sediments, stabilizing coastlines and building up stromatolitic reefs. Even without plants, the continents played an active role in shaping the biosphere. One of the most important aspects of Columbia's existence was its role in the carbon cycle. Weathering of rocks on land pulled carbon dioxide from the air, locking it into minerals that washed into the oceans. This process acted as a thermostat for Earth's climate. At times, it may have drawn down enough carbon dioxide to cool the planet, contributing to glaciations. At other times, volcanic outgassing restored balance by replenishing greenhouse gases. The continents, in this way, helped regulate Earth's temperature, even in a world without forests or soils. If you were to walk across Colombia, you would have seen vast expanses of exposed rock, occasional volcanic eruptions, and rivers winding through barren valleys. The air might have carried the sharp tang of volcanic gases, and the ground would have been littered with weathered stones. On the coasts, microbial mats would have been the only sign of life visible to the naked eye. It would have been a landscape both alien and familiar, earthly in its geology, but alien in its lifelessness. Though quiet compared to the lush continents of later times, Colombia was a crucial step in Earth's history. Its vast size influenced ocean currents, atmospheric circulation, and climate. Its weathering shaped the carbon cycle. Its presence altered the distribution of life in the oceans, creating new environments along its coasts. Even in its barrenness, Colombia was a stage on which the future drama of life would unfold. As you imagine this ancient supercontinent, think of the silence, the stark beauty of exposed stone, the slow carving of rivers into rock, and the patient work of microbes spreading across shorelines. It was a land without forests or animals, but it was alive in its own quiet way, preparing the ground for worlds yet to come. In the next chapter, we will explore the yars or geology of this era, the rocks and minerals that preserve clues about Earth 2 billion years ago, and what they tell us about the processes that shaped both land and sea. The geology of Earth 2 billion years ago is written into rocks that still stand today. These ancient stones are time capsules, preserving clues about the planet's surface, atmosphere, and life at the time. To a geologist, they are not lifeless artifacts but storytellers, layers of minerals, chemical signatures, and fossils of microbial mats that whisper what the world was like in this deep past. By studying them, we can reconstruct not only landscapes but also the invisible cycles of oxygen, carbon, and nutrients that shape the planet. The most iconic geological signature of this era is this banded iron formation, BFE. These are massive rock layers made of alternating bands of iron, rich minerals, and silica. They formed in the oceans, where dissolved iron interacted with oxygen produced by cyanobacteria. When oxygen levels rose in surface waters, iron oxidized and fell to the seafloor, forming iron-rich layers. When oxygen declined, silica dominated, forming lighter layers. Over millions of years, these cycles created vast sheets of rock that today supply much of the world's iron ore. Banded iron formations tell us that oxygen existed, but also that it fluctuated. Oxygen never spread evenly through the oceans, but instead appeared in waves, rising and falling with microbial blooms and environmental changes. The presence of these formations 2 billion years ago reveals that Earth was still in transition, caught between an anoxic past and an oxygen-rich future. Alongside iron, sulfur isotopes provide another geological window. Rocks from this time preserve unusual patterns of sulfur that form only in low oxygen conditions. These isotopes indicate that while oxygen reached the atmosphere and surface oceans, large portions of the deep seas remained anoxic and rich in hydrogen sulfide. Geologists call these conditions oxinic, meaning both oxygen-poor and sulfide-rich. Such environments were toxic to most life, but they created niches for sulfur-loving microbes. In the rocks, these isotopic signatures serve as fingerprints of ancient chemistry. Another key feature of the geology is the preservation of our stromatolites, layered mounds built by microbial mats. Stromatolites are among the oldest biological structures on Earth, and 2 billion years ago they flourished in shallow seas. Microbes, mainly cyanobacteria, trapped sediments and secreted sticky films, building layer upon layer over time. Some stromatolites reached impressive sizes, forming reef-like structures along coastlines. In the rock record, stromatolites appear as wavy, domed patterns, proof that microbial life was abundant and ecologically active. Continental geology from this time also tells a story. Sedimentary rocks deposited on land and in shallow seas preserve information about rivers, deltas, and lakes. Without plants to stabilize soils, sediments were transported differently. Erosion was slower but more direct, with weathering acting directly on bare rock. The minerals washed into rivers and oceans carried nutrients that fueled microbial life, but also altered the balance of atmospheric gases. These processes are recorded in mudstones, sandstones, and carbonates that geologists can still examine today. Volcanic rocks are another major part of the 2 billion-year-old record. Lava flows and ash layers reveal that volcanism was widespread, especially during the assembly of the supercontinent Columbia. Volcanic activity added carbon dioxide to the atmosphere and released trace metals like nickel and molybdenum, which microbes used in their metabolisms. These trace elements were critical for the evolution of life, and their presence in volcanic rocks gives us hints about the resources available in the oceans of the time. Metamorphic rocks also play a role in the story. Over billions of years, many rocks from this era were buried and transformed by heat and pressure, becoming schists, gneisses, and quartzites. Even so, their chemical compositions often retain traces of ancient processes. For example, ratios of certain isotopes in metamorphic rocks can tell us about weathering rates, volcanic activity, and the cycling of carbon between land, ocean, and atmosphere. One of the most remarkable tools geologists use is the study of stable isotopes, particularly carbon isotopes. The ratio of carbon-12 to carbon-13 in ancient rocks reflects how life and the environment interacted. 2 billion years ago, carbon isotope records suggest long periods of stability, interrupted by shifts that may reflect ice ages or changes in atmospheric oxygen. These stable isotope records are among the strongest pieces of evidence for the so-called boring billion, when Earth's environment was relatively steady for hundreds of millions of years. Geology also records the formation of supercontinents. Rocks from different continents show signs of having once been joined through matching mineral deposits, aligned mountain ranges, and paleomagnetic signatures that record the orientation of Earth's magnetic field. By comparing these clues, geologists reconstruct the existence of Columbia, the ancient landmass that dominated this era. Its formation and breakup are written into the geology of nearly every continent today. Fossil evidence beyond stromatolites is sparse, but there are hints of early eukaryotic life in microfossils preserved in shales. Some of these fossils show complex cell walls or larger sizes than typical bacteria, suggesting that eukaryotes were beginning to evolve and spread. Though small, these fossils represent monumental steps in biology, preserved in stone for us to study billions of years later. Altogether, the geology of 2 billion years ago tells a story of transition and stability. Transition because oxygen was rising, oceans were changing, and life was experimenting with new forms. Stability because for long stretches the balance of gases and nutrients held steady, allowing life to gradually adapt rather than being thrown into chaos. This combination of change and balance is what makes the era so fascinating. It was a time when Earth was preparing for future revolutions without yet undergoing them. As you reflect on these rocks, imagine walking through a canyon today and touching stones that are 2 billion years old. Each layer, each mineral, each band of iron or ripple of stromatolite is a message from a world unimaginably ancient. The geology is not just rock, it is memory, a record of a time when Earth was halfway to becoming the planet we know. In the next chapter, we will step from the rocks back into the realm of biology, exploring the microbial life that dominated Earth 2 billion years ago and how it shaped the atmosphere, oceans, and continents. 2 billion years ago, life on Earth was overwhelmingly microbial. No trees shaded the land, no animals swam in the oceans, no insects buzzed in the air. Instead, the world was ruled by bacteria and archaea, tiny single-celled organisms invisible to the naked eye, yet immensely powerful in their collective impact. These microbes were the architects of Earth's chemistry, the pioneers of ecosystems, and the quiet innovators who laid the foundations for complex life. The most important players of the time were cyanobacteria. These photosynthetic microbes use sunlight, water, and carbon dioxide to produce food, releasing oxygen as a byproduct. Cyanobacteria had already triggered the Great Oxidation event hundreds of millions of years earlier, filling the atmosphere with the first pulses of oxygen. By 2 billion years ago, they remained dominant in shallow waters, forming vast colonies in microbial mats and stromatolites. Each mat was a bustling city of microbes, layered like a cake, with cyanobacteria on top capturing sunlight and other bacteria beneath recycling nutrients. Stromatolites, the layered rock structures built by microbial mats, were some of the most visible signs of life. These domes and ridges dotted shallow coastlines, forming reefs that stabilized sediments and created habitats. Stromatolites grew slowly, layer by layer, as microbes trapped particles and secreted sticky films. Though simple in appearance, they represented ecosystems every bit as complex as modern coral reefs, only on a microscopic scale. Not all microbes used oxygen. In fact, most life at the time was still anaerobic, meaning it thrived in environments without oxygen. In deeper oceans, where oxygen could not penetrate, microbes used sulfur or iron instead. Some bacteria breathed sulfate, producing hydrogen sulfide in the process. Others oxidized iron, leaving behind distinctive mineral deposits. These anaerobic metabolisms filled niches in a chemically diverse world, recycling elements and fueling ecosystems far from sunlight. Archaea, distinct from bacteria, were also present. Many lived in extreme environments, such as hot springs or deep-sea hydrothermal vents. Some archaea produced methane as a metabolic byproduct, contributing to greenhouse warming in earlier times. By 2 billion years ago, methane was less dominant in the atmosphere, but methanogenic archaea still thrived in oxygen-poor environments. They were survivors of an older world, holding on to niches that oxygen could not touch. One of the most revolutionary developments of this era was the rise of eukaryotes, cells with internal compartments, including a nucleus. The earliest eukaryotic microfossils appear around 2 billion years ago, suggesting that this was when they first began to spread. Unlike bacteria, eukaryotes were larger and more complex. They could engulf other cells, store DNA in a protected nucleus, and manage energy more efficiently. These innovations would eventually make multicellular life possible, but for now, eukaryotes remained microscopic and rare. Still, their arrival marked a turning point in biology. Microbial life also played a role in shaping Earth's chemistry. By releasing oxygen, cyanobacteria changed the redox balance of the oceans and atmosphere. By using sulfur and iron, anaerobes altered the chemistry of sediments. By fixing nitrogen, converting atmospheric nitrogen into usable compounds, some microbes made essential nutrients available to ecosystems. In this way, microbes were not just passive inhabitants of Earth, they were engineers rewriting the chemistry of the entire planet. The diversity of microbial metabolisms was astonishing. Some microbes used light. Some used chemicals, some thrived in heat, others in cold, some in salty lakes, others in acidic springs. With no animals or plants to dominate ecosystems, microbes filled every available niche. They were the rulers of the planet, both in abundance and in influence. If you could look closely at a droplet of seawater from 2 billion years ago, you would see a teeming world. Filaments of cyanobacteria would weave through the water, forming mats and colonies. Tiny eukaryotes might drift nearby, feeding on smaller bacteria. Anaerobic microbes would cluster in darker, oxygen-free zones, invisible to the naked eye but critical to the recycling of nutrients. Every cubic centimeter of water would be alive, humming with microbial activity. Yet for all their activity, these microbes were largely invisible in the larger landscape. To the human eye, Earth 2 billion years ago might have seemed barren. Only stromatolites, microbial mats, and subtle discolorations in water would hint at the life swarming within. The quiet persistence of microbes gave the impression of stillness, even as they reshaped the atmosphere and oceans molecule by molecule. This microbial dominance would last for billions of years. Even today, microbes remain the most abundant and diverse form of life on Earth. But 2 billion years ago, they were not just dominant, they were exclusive. They held every niche, ran every ecosystem, and carried out every biochemical cycle. The rise of plants and animals lay far in the future. For now, microbes were the undisputed rulers of Earth. As you imagine this microbial world, picture coastlines slimed with mats of cyanobacteria, shallow lagoons filled with stromatolite reefs, and deeper waters bubbling with sulfur-loving bacteria. Picture hydrothermal vents surrounded by archaea, glowing faintly in the darkness. Picture early eukaryotes drifting quietly, carrying within them the spark of future complexity. It was a world of invisibility, yet also of immense activity, a planet alive on the smallest scales. In the next chapter, we will explore the food webs and ecosystems of this time, examining how microbes interacted with each other and how energy and nutrients flowed through this microbial Earth. When we think of ecosystems today, we imagine forests buzzing with insects, coral reefs swarming with fish, or grasslands alive with herds of animals. But 2 billion years ago, during Earth's boring billion, ecosystems looked entirely different. There were no trees, no fish, no animals at all, only microbes. Yet even in this seemingly simple world, intricate food webs existed, woven from the invisible interactions of single-celled life. These ancient ecosystems were subtle but vital, maintaining the balance of energy and elements that sustained the planet. At the base of every ecosystem is air's primary source of energy. For the boring billion, that role belonged to cyanobacteria. These photosynthetic microbes captured sunlight and used it to produce organic matter. They formed microbial mats in shallow waters, trapping sediments and building stromatolites. The mats were like microbial cities, layers upon layers of different organisms, each with a role to play. At the top, cyanobacteria bathed in sunlight, producing oxygen and food. Beneath them, other microbes took advantage of the waste products and low oxygen conditions. For example, deeper in these mats lived anoxygenic photosynthesizers, bacteria that used light but not oxygen. Instead of splitting water, they relied on sulfur compounds, producing hydrogen sulfide. Beneath them, still other microbes consumed hydrogen sulfide or methane, completing chemical cycles. The entire mat worked as a self-contained ecosystem, recycling nutrients in tightly woven loops. In open waters, as planktonic cyanobacteria floated freely, forming the base of broader food webs. They produced organic molecules that sank as detritus, feeding microbes in darker waters below. In oxygen-rich surface zones, aerobic microbes thrived, consuming organic matter and respiring oxygen. In deeper, oxygen-poor zones, anaerobic microbes took over, breaking down material through fermentation or by using sulfate or iron instead of oxygen. One of the most important nutrient cycles at this time was the sulfur cycle. Sulfate-reducing bacteria consumed organic matter and produced hydrogen sulfide, which could then be used by other microbes as fuel. This cycle created chemical gradients, zones where one group's waste became another's food. In modern ecosystems, we see similar dynamics in salt marshes, hydrothermal vents, and oxygen-poor lakes. 2 billion years ago, such cycles dominated entire oceans. Another crucial cycle was the iron cycle. In oxygen-poor but iron-rich waters, bacteria oxidized dissolved iron, producing rust-colored minerals that settled onto the seafloor. These processes contributed to the banded iron formations that still mark ancient rocks today. Each band of red and gray tells a story of microbes cycling iron, oxygen, and organic matter through invisible chemical loops. Even without plants or animals, as predation and grazing existed, early eukaryotes, which appeared around this time, were capable of engulfing bacteria through phagocytosis. This new form of interaction added complexity to ecosystems. Instead of relying solely on chemical recycling, some organisms fed directly on others. This was the earliest form of predator-prey dynamics, though played out entirely among microbes. Such interactions may have driven the evolution of defenses, such as protective cell walls, and innovations like mobility. These ecosystems were not static. They responded to changes in chemistry, climate, and geography. In shallow seas, microbial mats and stromatolites flourished, creating rich local ecosystems. In deeper basins, oxygen-poor conditions dominated, fostering anaerobic communities. Near hydrothermal vents, archaea and bacteria thrived on chemical energy, using hydrogen, methane, and sulfur. Across the planet, diversity emerged not from visible plants and animals, but from invisible microbes adapting to every chemical niche. Energy flow in these ecosystems was slower than in modern ones. Without large organisms to move nutrients quickly, cycles depended on microbial processes, which operated at microscopic scales. Yet this slowness also meant stability. The boring billion was marked by equilibrium, with ecosystems balancing inputs and outputs over long timescales. Oxygen levels stabilized, nutrient cycles persisted, and life endured in quiet continuity. The importance of nitrogen fixation also cannot be overstated. Cyanobacteria were among the first organisms to convert atmospheric nitrogen into ammonia, a form usable by living things. Without this process, ecosystems would have quickly run out of nitrogen, an essential element for proteins and DNA. Nitrogen fixers kept the cycle going, ensuring that life had the resources it needed to persist. Though microbial ecosystems may seem unimpressive compared to rainforests or coral reefs, they were the foundation for all future life. They enriched the oceans with oxygen, recycled nutrients, and built stable environments. Without this microbial groundwork, complex multicellular organisms could not have evolved later. The food webs of the boring billion were like scaffolding, temporary, but essential for the construction of a more complex biosphere. If you were to drift through the oceans of 2 billion years ago, you would see little with the naked eye. The water might appear murky, tinged green or red by blooms of cyanobacteria. In shallow lagoons you would find stromatolite reefs, strange, lumpy structures rising from the seafloor. The air might carry a faint tang of sulfur from bacterial activity. Yet beneath the surface, every drop of water would be alive with interactions. Cells dividing, gases exchanging, chemicals cycling. It was a hidden world of extraordinary resilience. This microbial web of life reveals a profound truth: ecosystems do not need complexity to be effective. Even without animals or plants, Earth's biosphere functioned balanced and thrived. The slowness of the boring billion was not a failure, but a demonstration of stability. Life had found a sustainable rhythm, one that would endure for 1 billion years until the stage was set for change. As you imagine drifting into rest, picture ancient seas humming with invisible life. Imagine microbial mats glowing faintly in shallow waters, their layers recycling sunlight into food and waste into nutrients. Imagine the first eukaryotes swimming quietly, feeding on smaller cells, beginning a new kind of interaction. The ecosystems of this time were silent and unseen, but they carried within them the seeds of all future life. In the next chapter, we will step into the geology of the era, exploring how continents, oceans, and tectonic movements shaped these ecosystems and left their marks in stone. The boring billion was not only a story of biology but also of geology. During this vast stretch of time, Earth's continents grew, stabilized, and began to take on the shapes we recognize today. The movements of tectonic plates, the assembly of supercontinents, and the creation of cratons provided the backdrop for life's quiet persistence. While the biosphere seemed stable, the solid Earth was in motion, shaping oceans, climates, and habitats. To understand the geology of this era, we must first picture Earth around 1.8 to 2.8 billion years ago. The surface was already divided into continents and oceans, but the continents were smaller, scattered, and in constant flux. Through the processes of plate tectonics, landmasses collided, merged, and broke apart, assembling the frameworks of future supercontinents. These tectonic dances not only rearranged geography, but also influenced the chemistry of oceans and the evolution of life. At the heart of these continents were cratons, ancient, stable blocks of continental crust that still exist today. Cratons formed earlier, during the Archean and early Proterozoic, and by the boring billion they acted as the bones of continents. They were thick, buoyant, and resistant to recycling back into the mantle. The Canadian Shield, the Kapval Craton in South Africa, and the Pilbara Craton in Australia are examples. These cratons provided stability, anchoring continents against the restless motion of tectonic plates. One of the defining geological events of the boring billion was the assembly of the supercontinent as Columbia, sometimes called Nunat. Around 1.8 billion years ago, collisions between cratons fused together a vast landmass stretching across much of the globe. Columbia may have been the first true supercontinent in Earth's history, larger and more integrated than earlier continental clusters. Its assembly produced immense mountain ranges, folded rocks, and deep, rooted structures still visible in ancient belts today. Over the next several 100 million years, Columbia gradually fragmented, only to see new collisions form another supercontinent, Rodinia, around 1.1 billion years ago. Rodinia brought together nearly all of Earth's land into a single enormous mass. Its center may have been what is now Laurentia, the ancient core of North America, with other cratons surrounding it in a giant jigsaw puzzle. For the biosphere, Rodinia's assembly meant new coastlines, changing ocean currents, and altered climates. For geology, it marked one of the great cycles of continental growth and breakup. These supercontinent cycles shaped the oceans of the boring billion. When continents clustered, vast inland seas formed, while ocean circulation slowed, often leading to stagnant waters low in oxygen. When continents broke apart, new seafloor spread, oceans opened, and chemical exchanges increased. This rhythmic assembly and breakup of continents influenced nutrient supply, oxygenation, and climate, subtly guiding the trajectory of life. Evidence of these ancient processes is preserved in orogenic belts, the scars of continental collisions. Rocks in these belts show the immense pressures and temperatures that once folded mountains miles high. Today they appear as worn-down ranges, eroded over billions of years. Yet their minerals reveal stories of deep burial, heat, and metamorphosis, testifying to the power of tectonic collisions. Another key feature of the era was igneous activity. Large igneous provinces, LIPs, massive outpourings of lava, erupted periodically across continents. These events reshaped landscapes and altered atmospheric chemistry by releasing gases. While less frequent than in earlier eons, LIPs during the boring billion contributed to the slow balance between carbon dioxide, oxygen, and other gases in the atmosphere. They also provided fresh rock surfaces for weathering, feeding nutrients into oceans and sustaining microbial ecosystems. Sedimentary rocks from this time provide glimpses of ancient environments. Sandstones, shales, and carbonates deposited in shallow seas record the slow accumulation of sediments over hundreds of millions of years. Unlike younger rocks, which often show signs of dramatic shifts, these layers are relatively uniform, reflecting the long stability of the boring billion. Stromatolite-rich carbonates reveal the presence of microbial mats, while banded iron formations signal the ongoing cycling of oxygen and iron. The stability of cratons also made the boring billion a time of mineral wealth formation. Many of the world's richest ore deposits, including nickel, copper, platinum, and rare earths, formed during this era, locked within stable crust. These resources, mined today, owe their origins to the slow, steady processes of tectonics and magmatism that operated billions of years ago. Geology and biology during this time were deeply interconnected. The weathering of continental rocks released phosphorus, an essential nutrient, into the oceans. However, because the supercontinents were stable and erosion was relatively slow, nutrient supply was limited. This scarcity may have been one reason biological innovation lagged, reinforcing the impression of a boring billion years. In truth, the balance of geology and biology created conditions of remarkable stability, even if they seemed uneventful compared to later explosions of life. Imagine standing on Rodinia during its peak. Around you stretch vast continental interiors, dry and arid far from the coasts. Inland seas shimmer in basins, bordered by microbial reefs rather than coral ones. Mountains rise from ancient collisions, their slopes eroding slowly into broad plains. Rivers carry sediments to shallow seas, where stromatolites grow in quiet lagoons. The air is thin with oxygen, but breathable enough for early eukaryotes to thrive in hidden waters. It is a world in motion, though the changes are measured in millions of years. The geology of the boring billion teaches us that slowness does not mean inactivity. Continents shifted, oceans opened and closed, mountains rose and fell. Cratons provided stability, but supercontinents brought cycles of assembly and breakup. The planet was dynamic, laying the groundwork for the more dramatic events to come. As you rest, picture Earth's continents drifting across ancient oceans, their cores solid and enduring, their edges colliding and breaking. Picture rivers winding across Rodinia, carrying sediments to quiet seas. Picture volcanoes glowing on distant horizons, their eruptions feeding the cycles of chemistry and life. Beneath the calm surface of biology, the solid Earth was alive with motion, shaping the stage for the next great chapters in planetary history. In the next chapter, we will dive into climate and atmosphere during the boring billion, exploring how greenhouse gases, oxygen, and the sun's faint light maintained a world of stability. When we imagine Earth 2 billion years ago, it is easy to think of a world alien to us. Its continents bare, its skies thin, and its oceans microbial. Yet the climate and atmosphere of the boring billion were surprisingly stable. While earlier times saw dramatic shifts, like the Great Oxidation event, and later times brought global-scale glaciations, the interval between 1.8 and 0.8 billion years ago was marked by equilibrium. This long stability is part of why geologists call it boring, though in truth it was anything but dull. At the beginning of the boring billion, Earth's atmosphere had already changed dramatically from its earliest days. Before the Great Oxidation event, oxygen was nearly absent, and methane dominated, giving the skies a hazy orange tint. By around 2.0 billion years ago, oxygen began to accumulate in small but steady amounts, while methane levels declined. This shift transformed both the chemistry of the atmosphere and the climate. During this billion-year stretch, oxygen levels remained relatively low compared to today. Estimates suggest concentrations hovered at about 1/10% of present atmospheric levels. That amount was enough to reshape ecosystems, allowing early eukaryotes to emerge, but not enough to fuel animals or complex multicellular life. For billions of microbes, however, this was the perfect balance. Oxygen was available, but large swaths of the ocean still remained anoxic, low in oxygen, and filled with other gases like hydrogen sulfide. The result was a layered ocean-atmosphere system where diverse metabolisms coexisted. Carbon dioxide, the most important greenhouse gas at the time, played a central role in stabilizing the climate. Levels were higher than they are today, though far lower than the extreme amounts on Venus. Combined with a fainter sun, the young sun produced about 85–90% of the energy it does now. This carbon dioxide kept Earth warm enough for liquid water. Without it, the planet might have been locked in permanent ice. With it, temperatures remained moderate, creating an environment where life could persist, if not yet flourish in complexity. The boring billion was remarkable for its absence of extreme climate swings. Before this era, Earth may have experienced glaciations and intense greenhouse phases. After it, between 720 and 635 million years ago, the planet endured snowball Earth events when glaciers may have reached the equator. But between 1.8 and 0.8 billion years ago, the climate was relatively even. No evidence suggests global-scale glaciation during this interval. Instead, the world maintained long-term warmth and stability. This stability had consequences for evolution. On the one hand, it prevented catastrophic collapses that might have driven rapid change. On the other, it may have limited evolutionary pressures, slowing the diversification of eukaryotes. In a sense, Earth's steady climate provided security, but also monotony. Life adapted comfortably, but it did not yet leap into complexity. One factor contributing to this stability was the carbon-silicate cycle, Earth's natural thermostat. When carbon dioxide levels rose, weathering of continental rocks accelerated, pulling CO out of the atmosphere and depositing it in sediments. When CO levels fell, weathering slowed and volcanic outgassing replenished it. Over millions of years, this feedback system kept Earth's climate within livable bounds. During the boring billion, with continents stabilized and erosion steady, this cycle maintained equilibrium with little drama. Another stabilizing influence came from the oceans. Vast and deep, the seas acted as heat reservoirs, absorbing energy during warm periods and releasing it during cooler ones. Ocean circulation patterns may have been slower than today, with fewer nutrient inputs from erosion, but they still distributed heat across the globe. Combined with higher greenhouse gases, this circulation ensured that even under a fainter sun, Earth remained habitable. Yet this calm did not mean uniformity. Regional climates varied, as they do today. Coastal areas near shallow seas likely experienced humid conditions, with microbial mats thriving in warm lagoons. Interiors of large continents like Rodinia were likely arid, deserts stretching across vast distances with little vegetation to break the monotony. Seasonal variations, driven by Earth's tilt and orbit, brought cycles of warmth and coolness. These regional differences provided diverse niches for microbial life. Clues about this ancient atmosphere and climate come from rocks. Carbon isotope ratios in sediments reveal shifts in carbon cycling, while sulfur isotopes trace oxygenation. Red beds, sedimentary rocks stained with iron oxides, indicate the presence of oxygen in the air. The absence of glacial deposits during this interval supports the idea of long-term stability. Together, these records paint a picture of a world balanced between extremes, neither frozen nor scorched. If you could stand on Earth during the boring billion, the air would feel familiar yet different. You could breathe it, though with difficulty. It would feel thin, like standing at a high altitude today. The skies would be blue, though hazier with more carbon dioxide. Clouds would drift much as they do now, and rains would fall across the land. Temperatures would be warm, seas calm, and glaciers absent. The world would seem deceptively modern, though life within it remained profoundly ancient. This climate and atmospheric stability made the boring billion a bridge. It connected the chaotic past of oxygen revolutions and methane hazes with the dramatic future of snowball Earth and animal evolution. Without this long period of balance, Earth may not have developed the steady conditions necessary for complex life to emerge later. The calm was not boring, it was foundational. As you drift into calm, imagine this ancient atmosphere surrounding the planet like a delicate veil. Picture blue skies stretched over continents of Rodinia, rains falling on stromatolite reefs, winds blowing across arid interiors. Picture an ocean breathing slowly with carbon and oxygen, stable yet alive. It was a world of quiet balance, a billion years of stability that made all the difference for the story yet to come. In the next chapter, we will look at the oceans during the boring billion, exploring how their chemistry, circulation, and oxygen levels shaped ecosystems and influenced the trajectory of evolution. If the continents of the boring billion were the stage, the oceans were the heart of the play. Covering most of the planet, they were the environments where nearly all life existed, the medium in which Earth's chemistry was balanced, and the cradle of early biological innovation. Yet these oceans were very different from the ones we know today. 2 billion years ago, their chemistry, circulation, and oxygen levels created conditions that were stable but profoundly alien compared to modern seas. The most striking feature of the oceans during this era was their rest oxygen profile. While oxygen was slowly building up in the atmosphere thanks to cyanobacteria, much of the ocean remained anoxic, low or devoid of oxygen. The surface layers, where sunlight penetrated, held enough oxygen to sustain cyanobacteria and some early eukaryotes. But deeper waters, shielded from the mixing effects of wind and currents, stayed oxygen poor. In many places, these deeper waters were also exonic, meaning rich in hydrogen sulfide. This toxic environment supported only specialized microbes that thrived on sulfur chemistry. This layering of the oceans into oxygen, rich surfaces and oxygen, poor depths is sometimes called the stratified ocean. It persisted for much of the Proterozoic and shaped both biology and chemistry. For microbes in shallow waters, conditions were ideal for photosynthesis. For life deeper down, survival depended on unusual metabolisms, sulfate reduction, iron cycling, and methanogenesis. These processes maintained ecosystems, but they also limited opportunities for more complex organisms to evolve. Nutrients were another key factor. In modern oceans, rivers deliver nitrogen and phosphorus from land, fueling plankton growth and supporting food webs. During the boring billion, erosion rates were lower, and nutrient inputs were smaller. The vast supercontinent Rodinia, with its stable cratons, did not provide as much fresh rock to weather. As a result, oceans may have been nutrient limited, particularly in phosphorus. This scarcity kept productivity relatively low, reinforcing the slow pace of biological change. Yet despite these limitations, the oceans were far from lifeless. Cyanobacteria flourished in surface waters, forming mats and reefs along coastlines. They not only produced oxygen but also fixed nitrogen, converting inert atmospheric nitrogen into usable forms that sustained ecosystems. Green algae, among the earliest eukaryotes, also began to appear in these shallow seas. Though simple, they marked the first steps toward more complex plant-like life. In deeper layers, sulfur bacteria and iron oxidizers thrived, creating chemical cycles that left their mark in sediments. The oceans were also sites of profound geological and chemical interactions. Hydrothermal vents along mid-ocean ridges released hot, mineral-rich water, feeding unique microbial communities. Black smokers spewing sulfides and metals provided niches where archaea and bacteria harnessed chemical energy rather than sunlight. These systems may have acted as refuges for life when surface conditions grew challenging, ensuring survival through the ages. Sedimentary rocks from this time preserve clues about these alien oceans, which had banded iron formations BFs, which had dominated earlier, declined during the boring billion but still appeared in some places. They record the cycling of oxygen and iron between surface and deep waters. Shales and carbonates, deposited in shallow seas, contain isotopic signatures of carbon and sulfur that reveal the balance of oxygen and microbial metabolisms. These chemical fingerprints tell us that the oceans were stable but stratified, productive but limited, alive but not yet diverse. One fascinating aspect of Proterozoic oceans is their connection to global climate. Oceans absorb and redistribute heat, and their chemistry influences greenhouse gases. During the boring billion, the oceans acted as a massive buffer, keeping carbon dioxide and oxygen in balance. They absorbed cal through weathering inputs, stored it in carbonates, and released it again through tectonic processes. This balance contributed to the climate stability that defined the era. If you could stand on a Proterozoic shoreline and look out to sea, the view might seem familiar at first. Blue waves would roll onto rocky coasts, clouds would drift overhead, and tides would rise and fall. But on closer inspection, differences would emerge. Beaches would lack plants or animals, no shells, no crabs, no birds. Instead, microbial mats would coat tidal flats, slimy and green offshore. Stromatolite reefs would rise in shallow lagoons, built not by corals but by layered bacteria. The water itself might carry a faint odor of sulfur, betraying the oxenic depths below. Beneath the waves, the ecosystem would be quiet compared to today's seas. No schools of fish, no whales, no bustling coral reefs. Instead, microbial life dominated, invisible to the naked eye but everywhere present. Algae and cyanobacteria would float near the surface, producing oxygen and organic matter. Bacteria in deeper waters would recycle sulfur and iron, maintaining chemical cycles. It would seem barren to human eyes. Yet it was a thriving world on its own terms. The oceans of the boring billion highlight the paradox of this time. On the surface, stability and monotony seemed to prevail. Yet beneath that calm, complex interactions unfolded, between oxygen and sulfur, between microbes and minerals, between tectonics and climate. These oceans were not lifeless waiting rooms but laboratories where the groundwork for future life was laid. As you drift into rest, imagine floating on one of these ancient seas. Picture waves lapping against microbial mats, the water below stratified into layers of oxygen and sulfur. Picture colonies of cyanobacteria glowing faintly in sunlight, while sulfur bacteria thrive in the depths. Picture hydrothermal vents in the darkness, releasing plumes of heat that sustain unseen life. The oceans may not yet have hosted fish or whales, but they were alive in every drop. In the next chapter, we will turn from the oceans back to the Ars landscapes of the continent Seer, exploring what Earth's surface looked like above sea level during the boring billion. When we think of Earth's continents today, we picture forests, grasslands, deserts, and bustling ecosystems filled with plants and animals. 2 billion years ago, however, the continents looked nothing like this. The land of the boring billion was barren, rocky and quiet, shaped only by wind, rain, and microbes. No trees shaded the land, no flowers bloomed, no animals roamed. The landscapes of this time were stark, but they were also dynamic, constantly being eroded, weathered, and reshaped by the forces of geology and climate. At the broadest scale, the continents were already assembled into large landmasses, eventually joining into the supercontinent Hasrodinia around 1.1 billion years ago. These landmasses were made up of avhutans, ancient and stable cores of continental crust, stitched together by mountain belts formed from collisions. The interiors of these continents were vast and dry, far from the moderating influence of the oceans. Rainfall rarely reached deep inland, and with no plants to hold soil, erosion was slow and uneven. The coastlines, by contrast, were where most of the action took place. Shallow seas lapped against rocky shores, flooding continental shelves and creating broad tidal flats. These flats were not empty. They were coated with vast microbial mats, slimy layers of cyanobacteria that trapped sediments and built stromatolites. Along these coastlines you would see reef, like ridges of stromatolites rising in lagoons, forming some of the earliest complex ecosystems. Though lacking animals, these mats were bustling with microbial activity, recycling nutrients and producing oxygen. Inland landscapes were far harsher. With no vegetation, rivers were flashy and unstable. When rains fell, they eroded rocks directly, creating braided channels choked with sediments. Floods carried boulders downstream, leaving behind rocky beds. Between rivers stretched deserts, broad expanses of bare rock, sand, and dust. Winds whipped sediments across open plains, creating dunes much like those in today's deserts. Without roots to anchor soil, landscapes shifted quickly under the force of water and air. Mountains also rose across the continents, especially during the collisions that formed supercontinents like Columbia and Rodinia. These ranges would have been massive when first created, rivaling the Himalayas. Over millions of years, however, they eroded, their sediments washed into seas. The exposed rocks of these mountains told stories of immense pressures and temperatures, recording the assembly of continents. From the perspective of life, these mountains were empty stone giants, but from the perspective of geology, they were milestones in Earth's history. Lakes occasionally formed in basins, but they were unusual compared to modern lakes. With no plants to stabilize shorelines or filter runoff, waters often became saline or filled with dissolved minerals. Microbial mats thrived in such lakes, just as they did along coastlines. These environments left behind distinctive chemical signatures, including carbonate deposits that preserved the traces of microbial life. Another feature of the continents was volcanism. Throughout the Boring Billion, large igneous provinces erupted periodically, flooding landscapes with basaltic lava. These eruptions reshaped surfaces, created new crust, and released gases that influenced the atmosphere. Though destructive locally, they also provided fresh rock surfaces for weathering, feeding nutrients like phosphorus into rivers and oceans. In this way, even barren volcanic fields contributed to the cycles of life. One might wonder, was the land completely lifeless? For the most part, yes. Plants would not appear until about 470 million years ago, and animals until even later. But there is some evidence that microbial mats extended beyond coastlines, colonizing moist soils or rock surfaces. These early land-based microbes may have formed dark crusts on rocks, much like lichens and cyanobacteria do today in deserts. If so, they were the pioneers of terrestrial life, anchoring the first ecosystems on land long before plants arrived. The visual appearance of the continents would have been striking to us. Imagine standing on the shore of Rodinia. Behind you, mountains rise from ancient collisions, their slopes bare and rocky. Inland stretches a desert plain, dunes shifting under relentless winds. Ahead lies a shallow sea, dotted with stromatolite reefs. The sky is hazy, the air thin with oxygen but breathable. Rain falls in sudden bursts, carving channels that dry quickly under the sun. It is a world both familiar and alien, shaped by the same geological forces we know, yet devoid of the living landscapes we take for granted. Despite their barren appearance, these continents played a critical role in Earth's systems. Their weathering regulated atmospheric carbon dioxide, their erosion supplied nutrients to oceans, and their collisions created mountains and supercontinents that altered climate and circulation. The land may not have hosted forests or animals, but it was far from irrelevant. In its quiet, the continental surface set the stage for the future greening of Earth. As you imagine these landscapes, picture their silence. No bird calls, no rustling leaves, no insect hum. Only the sound of wind over rock, rain on bare ground, and waves against stromatolite reefs. Picture rivers rushing after storms, then drying into braided channels. Picture dunes shifting endlessly, sculpted by unseen hands. This was Earth during the Boring Billion, harsh on the surface, yet alive with potential, waiting for life to spread beyond the seas. In the next chapter, we will explore the tectonic activity of this time, examining how the assembly and breakup of supercontinents shaped both land and ocean environments. The continents we know today, Africa, Asia, the Americas, Antarctica, and Europe, are fragments of a much deeper story, one written in cycles of collision and separation. 2 billion years ago, during the period often called the Boring Billion, Earth's continents were not static. They drifted, collided, and assembled into massive supercontinents, only to break apart again. These tectonic cycles shaped the oceans, atmosphere, and climate, even if the world seemed outwardly stable. To understand this, we need to recall that Earth's crust is divided into tectonic plates. These plates float on the semi-fluid mantle beneath, moving at just a few centimeters per year. Over millions of years, however, such small movements add up to immense rearrangements of the planet's surface. During the Boring Billion, these motions created at least two great supercontinents, as Columbia, also called Nuna and later as Rodinia. Around 1.9 to 1.8 billion years ago, the first known supercontinent, Columbia, assembled. Cratons, ancient fragments of continental crust, collided and sutured together, forming mountain ranges that rivaled today's Himalayas. These collisions were not sudden but drawn out, lasting tens of millions of years. Rivers carried sediments from the rising mountains, depositing them in vast basins. The supercontinent stretched from pole to pole, covering much of Earth's surface. Its interior regions would have been harsh, dry, and desert-like, far removed from the moderating influence of oceans. Along its margins, shallow seas teemed with microbial mats, stromatolites, and oxygen-producing cyanobacteria. Columbia may not have had forests or animals, but it was already shaping Earth's future. Supercontinents do not last forever. Heat from Earth's mantle builds up beneath their massive bulk, eventually weakening and fracturing them. By about 1.5 billion years ago, Columbia had begun to rift apart, creating new oceans between its fragments. These oceans shifted currents, redistributed heat, and altered global climates. But the breakup was only temporary. Around 1.3 to 1.1 billion years ago, continental fragments once again drifted together, assembling into a new supercontinent as Rodinia. This process, known as the supercontinent cycle, would repeat throughout Earth's history. Each cycle lasted hundreds of millions of years, driving the long-term evolution of oceans, climates, and life. Rodinia was larger and more stable than Columbia. It existed from about 1.1 billion years ago until roughly 750 million years ago, straddling the equator. This position influenced both climate and circulation. Warm equatorial waters surrounded the continent, while polar regions remained relatively isolated. Rodinia's assembly created enormous mountain belts as continents collided. These mountains eroded slowly, feeding nutrients into the oceans. This steady nutrient supply may have supported microbial life, but it was not enough to spark rapid evolutionary change. Instead, Earth entered one of its longest periods of relative geological and biological stability, the Boring Billion. Rodinia's interior would have been vast and barren, dominated by deserts and rocky plains. Along its coasts, shallow seas supported microbial communities. The lack of higher life meant these environments were not as biologically rich as later ecosystems, but they were far from empty. Stromatolite reefs, microbial mats, and cyanobacterial colonies flourished, quietly reshaping Earth's atmosphere through photosynthesis. Tectonic activity during this time influenced climate in several ways. Volcanic eruptions released carbon dioxide, warming the planet, while the weathering of mountains consumed carbon dioxide, cooling it. This balance helped maintain Earth's climate in a relatively stable state. Unlike later eras, the planet did not experience massive swings into snowball Earth, glaciations. Instead, global temperatures remained warm and steady for much of the Boring Billion. The stability of climate and tectonic activity is part of why this period seems boring, compared to other chapters in Earth's history. Yet this very stability may have been critical for the slow, steady development of life. Without catastrophic shifts, ecosystems had time to adapt, diversify, and gradually prepare for later evolutionary leaps. We know about these tectonic events from the rocks left behind. Ancient mountain belts preserve the scars of collisions, while rift valleys and volcanic basalts record the opening of new oceans. Paleomagnetic studies, measuring the orientation of magnetic minerals in rocks, reveal how continents drifted across the globe together. These lines of evidence allow scientists to reconstruct the supercontinents of the distant past. Though invisible to the organisms of the time, plate tectonics shaped every aspect of their world. It determined the locations of shallow seas, the supply of nutrients, the circulation of oceans, and the chemistry of the atmosphere. It was the stage upon which microbial life played its part, even if no animals or plants yet existed. Imagine standing on the shore of Rodinia around 1 billion years ago. Towering mountains loom in the distance, their peaks eroding slowly into rivers that carry sediments to the sea. Vast deserts stretch inland, dry and windblown. Offshore shallow seas glimmer in the sun, filled with microbial reefs. The air is quiet, the land barren, but beneath your feet, the earth is alive with motion. Rodinia drifts slowly, inexorably reshaping the future. The supercontinent cycle is not unique to the Boring Billion. Later supercontinents, Pangaea, Gondwana, and others, followed the same pattern. But the cycles of this era stand out for their stability. Rodinia's long lifespan may have slowed the pace of environmental change, contributing to the impression of geological monotony. Yet beneath that monotony lay a steady engine of transformation, laying the groundwork for everything that followed. The continents of the boring billion may have seemed lifeless compared to today, but they were anything but irrelevant. Their collisions and breakups shaped oceans, regulated climate, and influenced the slow build-up of oxygen. They were silent architects of Earth's long story. In the next chapter, we will turn to the ocean chemistry and circulation patterns of this time, exploring how tectonics and climate together shaped the seas where most life still resided. When we think of Earth 2 billion years ago, it is tempting to imagine oceans that look like those of today. Blue, teeming with fish, currents swirling in complex patterns. But in truth, the seas of the boring billion were alien. They were the cradle of life, but their chemistry and circulation were unlike anything modern creatures would recognize. To understand this period, we must dive beneath the waves and explore the oceans as they truly were. 2 billion years ago, there were no fish, no corals, no kelp forests swaying in the current. Instead, life consisted almost entirely of microbes. Bacteria and archaea ruled the seas, forming mats, colonies, and free-floating cells. Stromatolites, layered structures built by cyanobacteria, rose from shallow seafloors, resembling bulbous rocks. These microbial communities shaped their environment, producing oxygen, capturing carbon, and altering the chemistry of seawater. But even as cyanobacteria released oxygen through photosynthesis, the oceans themselves remained mostly anoxic, oxygen-poor, for much of the boring billion. Oxygen struggled to penetrate deeper waters, leaving large parts of the ocean hostile to aerobic organisms. The oceans of this era were raw stratified, meaning that surface waters were very different from the depths below. Surface waters received sunlight, allowing photosynthetic microbes to thrive. These layers contained some oxygen, though still far less than today. Deeper waters cut off from mixing were oxygen-starved. Instead, they often contained hydrogen sulfide, a toxic gas produced by sulfate-reducing bacteria. These actinic sulfur-rich conditions may have stretched across vast regions of the seafloor. Imagine standing on a shoreline, looking out across calm seas, unaware that beneath the surface lay suffocating waters filled with sulfur compounds. To any complex life, had it existed, these oceans would have been lethal. Nutrients like phosphorus, iron, and nitrogen played critical roles in these ancient oceans. Unlike today, where upwelling currents and rivers constantly recycle nutrients, the boring billion seas often locked nutrients away in sediments. This limited the productivity of ecosystems, keeping oxygen levels low. Iron, in particular, tells the story of these waters. Ancient rocks preserve us banded iron formations. Layers of iron oxide that formed when dissolved iron in the oceans reacted with oxygen produced by microbes. These rocks are a record of fluctuating oxygen levels, showing times when oxygen briefly expanded into the oceans, only to retreat again. Phosphorus, another key nutrient, was often scarce. Without abundant phosphorus, photosynthetic microbes could not multiply rapidly, slowing the pace of oxygen production. This nutrient limitation may have been one reason why oxygen levels plateaued during the boring billion. Modern oceans circulate thanks to winds, tides, and differences in temperature and salinity. But during the boring billion, circulation was sluggish, with fewer temperature contrasts between equator and poles, and without large ice caps driving strong ocean currents, water movement was more stagnant. This sluggish circulation made it harder for oxygen to penetrate deep waters. Once again, surface layers remained habitable for microbes, while the depths became chemical sinks dominated by sulfur and iron. The oceans were layered, stable, and resistant to change. One of the most striking ideas about boring billion seas is that they may have been purple. Certain bacteria, called purple sulfur bacteria, thrived in oxygen-poor but sulfur-rich waters. These microbes used sunlight for photosynthesis, but instead of producing oxygen, they used sulfur compounds. Their pigments gave the water a reddish-purple tint. If you could look down from space 2 billion years ago, the oceans might not have been the deep blue we know today, but streaked with strange colors: green, red, purple, depending on which microbes dominated a given region. It was a world of microbial chemistry on a planetary scale. The chemistry of these oceans shaped the course of evolution. For complex life to emerge, higher oxygen levels were needed. But during the boring billion, nutrient scarcity, stagnant circulation, and sulfide-rich depths kept oxygen low. Eukaryotes, the more complex cells that would later give rise to plants and animals, already existed, but they struggled to diversify in such hostile seas. This does not mean the oceans were biologically boring. Microbes experimented endlessly with metabolism using light, sulfur, iron, or methane to survive. These innovations laid the foundation for future ecosystems. The oceans were microbial laboratories, even if they lacked visible diversity. How do we know about these ancient ocean conditions? The answer lies in sedimentary rocks. Layers of shale, carbonate, and iron-rich deposits preserve chemical fingerprints of the seas they formed in. Sulfur isotopes reveal the extent of oxenic waters. Heavy iron speciation shows how oxygenated or anoxic sediments were. Our trace metals, like molybdenum and vanadium, indicate how nutrients cycled. By piecing together these clues, scientists reconstruct a picture of oceans where oxygen was scarce, nutrients were limited, and circulation was sluggish. The stability of these ocean conditions is striking. For hundreds of millions of years, Earth remained in this state, oxygen at moderate levels, ocean stratified, microbes dominant. It was a world balanced on the edge of change, waiting for something to tip the scales toward greater complexity. Perhaps it was tectonic shifts that altered nutrient supply. Perhaps it was subtle evolutionary innovations in microbes. Whatever the triggers, the chemistry of the oceans during the boring billion set the stage for the eventual rise of animals hundreds of millions of years later. As you drift into rest, imagine floating on the calm seas of 2 billion years ago. The water looks strange, perhaps tinted purple or green by microbial pigments. The surface is warm, the air thin in oxygen. Beneath you lies a silent, toxic abyss filled with sulfur and iron. The oceans seem stable, eternal, unchanging. Yet within them, microbes quietly prepare the way for life's future. 2 billion years ago, Earth's landscapes and shorelines looked alien to modern eyes. There were no forests, no grasses, no animals crawling across beaches. Instead, life was dominated by us microbial mats, dense, carpet-like layers of microorganisms that thrived wherever water met rock or sediment. Among the most striking of these mats were harsh stromatolites, layered structures built by microbes that still stand today as some of the oldest living fossils. During the so-called boring billion, these mats and stromatolites were the visible face of life on Earth, and they played a central role in shaping the environment. Microbial mats were communities of microorganisms, mostly bacteria, that grew together in thin but resilient sheets. They covered tidal flats, shallow lagoons, and even some subtidal environments. These mats contained different layers, each hosting microbes with unique metabolisms. Cyanobacteria in the surface layers captured sunlight, performing photosynthesis and releasing oxygen. Beneath them, as anoxygenic bacteria thrived in low oxygen conditions, often using sulfur or iron for energy. Deeper still, other microbes decomposed organic matter, recycling nutrients back into the mat. Each layer was only millimeters thick, yet together they created a self-sustaining ecosystem. A microbial mat was like a miniature world, cycling energy and nutrients on a small but vital scale. Perhaps the most iconic structures from this time were stromatolites. These are layered mounds, columns, or sheets formed by microbial mats trapping and binding sediments. Over time, layer upon layer built up into stone-like domes. Stromatolites flourished across shallow seas during the boring billion. They dotted coastlines, spread across reefs, and created vast microbial landscapes. If you had waded into a tidal flat 2 billion years ago, you would have walked among fields of stromatolites rising like rounded rocks from the water. Remarkably, stromatolites still exist today, in places like Shark Bay in Western Australia and certain hypersaline lagoons. These modern stromatolites give scientists living examples of how ancient microbial communities worked. They are time machines, showing us how life looked billions of years ago. Cyanobacteria within microbial mats and stromatolites were among the first organisms to produce oxygen through photosynthesis. By capturing sunlight and splitting water molecules, they released oxygen as a byproduct. During the Great Oxidation event, this oxygen began to accumulate in the atmosphere. But even afterward, during the boring billion, stromatolites remained crucial contributors. They produced oxygen at local scales, helping oxygenate surface waters and slowly feeding the atmosphere. Without their steady output, Earth's air might never have reached levels sufficient for complex life. Imagine entire coastlines covered in mats, each sheet of microbes bubbling oxygen into the shallow seas. These tiny organisms were reshaping the entire planet molecule by molecule over millions of years. Microbial mats were more than oxygen factories. They acted as ecosystem engineers. By binding sediments together, they stabilized shorelines and created habitats for other microorganisms. Their sticky surfaces trapped particles carried by waves, forming microenvironments rich in nutrients. Stromatolites also influenced ocean chemistry. As they grew, they interacted with calcium and carbonate ions in seawater, often precipitating limestone. This helped regulate carbon dioxide levels and shaped the mineral record that geologists study today. In this way, stromatolites were not passive features of the environment. They actively reshaped it. Stromatolites were abundant during the Boring Billion, but after about 1 billion years ago, their numbers declined dramatically. Why? Scientists think the rise of grazing organisms, early animals like sponges and later mollusks, played a major role. These creatures scraped surfaces for food, disrupting mats and preventing stromatolites from flourishing. But during the Boring Billion itself, no such grazers existed. Microbial mats and stromatolites could grow undisturbed, spreading across coastlines and shallow seas. This period represents their golden age, when they were the undisputed rulers of Earth's ecosystems. How do we know stromatolites and mats were so widespread? The answer lies in rocks. Stromatolite fossils are preserved in ancient carbonate formations worldwide. Their distinctive domed or columnar shapes make them easy to recognize, even in rocks over 2 billion years old. In addition, certain chemical signatures, such as carbon isotopes, suggest widespread photosynthesis during this era. These isotopes act like fingerprints, showing how microbial mats altered the global carbon cycle. The rocks, layered with microbial structures and chemical traces, preserve the story of mats that covered Earth's shorelines for hundreds of millions of years. The Boring Billion has often been portrayed as a time of evolutionary stagnation, with little apparent change in life or climate. But for microbial mats and stromatolites, it was a time of abundance. They ruled unchallenged, thriving in stable conditions. To them, the Boring Billion was anything but dull. From a microbial perspective, it was a golden age. Sunlight, nutrients, and shallow seas provided everything they needed. These mats quietly sustained Earth's biosphere, laying the groundwork for more complex ecosystems that would eventually follow. As you close your eyes, picture a shoreline 2 billion years ago. Instead of sand dunes and seaweed, you see vast carpets of microbial mats stretching as far as the eye can see. Small domes of stromatolites rise above the waterline. Catching the glow of the sun, bubbles of oxygen rise silently from the mats, drifting into the air. The scene is quiet, slow and steady, life at its simplest, yet also at its most transformative. In their unassuming way, these microbes were preparing the stage for everything to come. Forests, animals, and humans owe their existence to these ancient mats. They remind us that even the smallest forms of life can change the fate of a planet. When we imagine Earth 2 billion years ago, we are relying on fragments of evidence written in stone. There are no fossils of animals, no trees preserved in amber, no footprints pressed into ancient mud. Instead, scientists must turn to us geological records, rocks, isotopes, and subtle chemical signatures to reconstruct the world of the Boring Billion. These natural archives provide a window into ancient oceans, atmospheres, and ecosystems, telling us what life and environment were truly like. Rocks are more than hardened minerals. They are SARS time capsules, preserving chemical and structural clues about the conditions in which they formed. Geologists study layers of sedimentary rock to understand past climates, ocean chemistry, and even biological activity. During the Boring Billion, many of the rocks that formed were as carbonates and shales. Carbonates, such as limestone, often preserve stromatolite structures, fossilized microbial mats that thrived in shallow seas. Shales, rich in organic matter, hold chemical fingerprints of oxygen levels and nutrient cycling. Together, these rocks act as pages in Earth's deep history book. Beyond the visible layers, scientists analyze as isotopes, atoms of the same element with different masses. Isotopic ratios act like fingerprints, revealing processes that shaped Earth's chemistry. As carbon isotopes Z-C and HC shifts in carbon isotope ratios show changes in the global carbon cycle. Photosynthesis, for example, prefers lighter carbon, leaving behind a signal in rocks. These signals tell us about productivity in ancient oceans. Sulfur isotopes AS and TARS's variations reveal the presence of sulfate, reducing bacteria, and the extent of oxinic sulfur, rich conditions in oceans. Oxygen isotopes O and ATO ratios can indicate temperature and the presence of glaciations, helping reconstruct climate conditions. Iron isotopes provide clues about oxygenation events, since dissolved iron reacts with oxygen to form oxides that settle into sediments. Through isotope analysis, scientists can piece together an image of ancient Earth's oceans and atmosphere without ever seeing them directly. One of the most striking rock records from this era is West-banded iron formations, BICES. These rocks consist of alternating layers of iron, rich minerals, and silica, often in striking red and gray bands. They formed when oxygen produced by microbes reacted with dissolved iron in the oceans, causing iron to precipitate and sink to the seafloor. BFs are essentially the fingerprints of early oxygenation. They show that oxygen was being produced in surface waters, but not yet widespread in the deep ocean. The persistence of BFs into the boring billion suggests that oceans remained stratified, with oxygen-rich shallows above and anoxic depths below. Certain trace metals, like molybdenum, vanadium, and chromium, are sensitive to oxygen levels. When oxygen is scarce, these metals behave differently than when it is abundant. By measuring their concentrations in ancient sediments, scientists can estimate how much oxygen was present in seawater. For example, molybdenum tends to accumulate in oxygen-rich waters. Low levels in boring billion shales indicate that deep oceans were largely oxygen-poor. These proxies confirm what isotopes already suggest: oxygen was limited, and microbial processes dominated ocean chemistry. Though the boring billion lacked animal fossils, it does preserve microfossils and chemical biosignatures. Under microscopes, scientists have found microscopic spheres and filaments in ancient rocks, believed to be remains of bacteria and early eukaryotes. More subtle are as biomarkers, organic molecules left behind by ancient organisms. Certain molecules like steranes are associated with eukaryotic cells. Their presence in rocks from this era suggests that complex cells had already evolved, even if they had not yet diversified widely. Geological records also tell us about climate stability during the boring billion. Oxygen isotopes from carbonates suggest relatively warm, stable conditions with few signs of global ice ages. Unlike later periods when Earth froze over in snowball Earth events, the boring billion appears to have been a long stretch of moderate climate. This stability may explain why life evolved so slowly. There were fewer environmental disruptions to drive rapid change. Reconstructing Earth's environment from 2 billion years ago is no simple task. Rocks that old have often been metamorphosed, heated and compressed until original features are obscured. Geologists must carefully separate original signals from later alterations. Despite these challenges, multiple lines of evidence, from isotopes to trace metals to fossils, all point to the same conclusion. Earth's oceans were stratified, oxygen levels were limited, and microbial life dominated. Without rocks and isotopes, the boring billion would remain a blank stretch in Earth's history. Instead, we now know it was a time of delicate balances, oxygen rising but not yet abundant, eukaryotes emerging but not yet flourishing, climate stable but not yet varied. These records remind us that progress in evolution is not always rapid. Sometimes Earth spends vast stretches of time in equilibrium, with life quietly maintaining stability rather than surging ahead. As you rest, picture geologists carefully studying ancient rocks, slicing them thin to peer at microscopic structures, measuring isotopes with delicate instruments. Imagine them piecing together a puzzle billions of years old. The rocks you might pass on a hike could hold whispers of ancient seas, stromatolites, and microbial life. These stones are not silent, they are storytellers. They carry the memory of Earth's long, steady heartbeat during the boring billion. Life needs more than water and sunlight. It also depends on as nutrients, the chemical building blocks that organisms use to grow, reproduce, and evolve. On modern Earth, nutrients like phosphorus, nitrogen, and iron flow through ecosystems in endless cycles, supporting forests, coral reefs, and ocean currents. But 2 billion years ago, during the boring billion, nutrients were often in short supply. This scarcity acted as an evolutionary bottleneck, slowing the rise of complex life and locking Earth into a long period of stability. Phosphorus is one of the most important elements for life. It forms the backbone of DNA and RNA, builds cell membranes, and powers metabolism through molecules like ATP. Without phosphorus, cells cannot divide or sustain themselves. During the boring billion, however, phosphorus was scarce. Most of it was trapped in continental rocks, slowly weathered and carried into the oceans. But warm, stable climates and limited glaciation reduced weathering rates, meaning fewer nutrients reached the seas. This shortage limited photosynthetic microbes like cyanobacteria. With less phosphorus, their growth slowed, reducing oxygen production. In turn, low oxygen limited the spread of eukaryotes, which require more energy and nutrients than bacteria. Earth's biosphere was caught in a cycle of scarcity, enough to sustain microbial mats and stromatolites, but not enough to fuel rapid evolutionary leaps. Nitrogen is another essential nutrient, critical for proteins and genetic material. On modern Earth, nitrogen cycles between the atmosphere, soils, and oceans through a mix of biological and geological processes. But in the boring billion oceans, nitrogen was not always easy to access. The atmosphere was full of nitrogen gas but only certain microbes could fix it into usable forms like ammonium or nitrate. These nitrogen-fixing microbes were vital, but their work was often hampered by the chemical state of the oceans. In oxygen-poor waters, fixed nitrogen was easily lost through processes like denitrification, where microbes converted nitrates back into nitrogen gas. This meant that just as nitrogen became available, it was quickly removed again. The result was a constant struggle for balance. Life was never starved completely, but it was rarely well fed. Iron also played a critical role. Early in Earth's history, iron was abundant in the oceans, dissolved in their anoxic depths, but as oxygen increased, iron reacted to form insoluble oxides, sinking to the seafloor. This process created banded iron formations, but also stripped iron from seawater, reducing its availability for microbes that depended on it for metabolism. Some microbes adapted by turning to other elements, like sulfur, for energy. But the overall effect was the same. Nutrients that once flowed freely became increasingly locked away, making life's expansion more difficult. Together, these nutrient shortages created what scientists call evolutionary bottlenecks. Eukaryotes, cells with nuclei and internal complexity, had already evolved by 2 billion years ago. Fossil and chemical evidence suggests they were present, quietly existing alongside bacteria. But they did not diversify widely. Why? Because eukaryotes are expensive organisms. They require more energy and nutrients than bacteria. They thrive in oxygen-rich, nutrient-rich environments, neither of which was common during the boring billion. Nutrient scarcity effectively held back their potential, forcing them to remain rare and limited until conditions improved hundreds of millions of years later. Although the boring billion was stable, it was not static. Small shifts in tectonics, weathering, and ocean chemistry sometimes increased nutrient availability. These surges may have allowed brief expansions of eukaryotic diversity, glimpses of the potential that would one day be realized. But overall, the balance of scarcity persisted. It was only later, as supercontinents broke apart, climates shifted, and glaciers spread across the world, that nutrient cycles changed dramatically. These disruptions replenished oceans with phosphorus and nitrogen, fueling the rise of complex life and eventually leading to the Cambrian explosion. The evidence for nutrient limitation comes from careful analysis of ancient rocks. Phosphorus content in shales provides direct evidence of how much was available to ecosystems. Low levels during the boring billion suggest scarcity. Nitrogen isotopes reveal how nitrogen cycled, showing the fingerprints of nitrogen fixation and denitrification in ancient oceans. Similarly, trace metal concentrations, like molybdenum and iron, indicate how nutrients were locked away or made available. These chemical records align to tell a consistent story. Life, during the boring billion, lived under nutrient constraints, shaping its slow evolutionary pace. The story of nutrient scarcity 2 billion years ago carries lessons for the present. Today, human activity is altering nutrient cycles on a massive scale. Fertilizers add excess phosphorus and nitrogen to rivers and seas, causing algal blooms and dead zones. While ancient life struggled under scarcity, modern ecosystems struggle under overabundance. In both cases, balance is key. As you drift into sleep, imagine standing by a shallow lagoon 2 billion years ago. Stromatolites rise like rounded mounds. Microbial mats stretch across the shore, and the air is thin with oxygen. Beneath the calm surface, life struggles not with predators, but with scarcity. Phosphorus is rare, nitrogen slips away, and iron is locked in stone, yet slowly, patiently, life persists. Though limited, these microbes hold the thread of continuity. They are the ancestors of everything that would come after. Forests, animals, and eventually us. Their quiet endurance, despite scarcity, is a lesson in resilience, a reminder that life does not always flourish quickly, but it always endures. When scientists describe the boring billion, they often highlight not just the slow pace of biological evolution, but also the remarkable stability of Earth's climate. Between about 1.8 and 0.8 billion years ago, Earth avoided the dramatic swings that marked other chapters of its history. There were no catastrophic snowball Earth, glaciations, no sudden bursts of oxygen, no mass extinctions. Instead, the climate remained steady, warm, and balanced for nearly a billion years. This stability may sound uneventful, but it was central to shaping Earth's evolutionary trajectory. Before the boring billion, Earth had already endured great changes. The Great Oxidation event had transformed the atmosphere, and earlier ice ages had left their mark on the rock record. After the boring billion, Earth would plunge into snowball Earth events and later experience rapid evolutionary bursts. But during the boring billion itself, conditions seemed almost tranquil. Average global temperatures were likely warm, with shallow seas covering much of the continents. There is little evidence for widespread glaciation, and oxygen levels remained steady at moderate levels. It was as though Earth found a balance point, a long interlude of calm between storms. Part of this stability came from the arrangement of continents. Around 1.8 billion years ago, land masses assembled into the supercontinent, Columbius or Nuna. Later, around 1.3 billion years ago, they reassembled into another supercontinent, Rodinia. Supercontinents regulate climate in several ways. They reduce coastlines, limiting the exchange of carbon between oceans and atmosphere. They stabilize ocean circulation by altering basin shapes. They moderate tectonic activity by locking continents into large, stable blocks. These factors slowed the cycling of carbon and nutrients, reducing the chances of sudden climate swings. In effect, the supercontinents acted like anchors, holding Earth's climate in place. The West carbon cycle is one of the main engines of climate regulation. On modern Earth, carbon dioxide levels rise through volcanic activity and fall through processes like weathering and the burial of carbon in sediments. These shifts often drive ice ages and warming events. During the boring billion, however, the carbon cycle appears to have been unusually balanced. Rocks from this period show relatively stable carbon isotope ratios, suggesting few major disruptions in carbon burial or release. With neither excessive greenhouse warming nor runaway cooling, Earth maintained a steady, temperate climate. The atmosphere, too, seems to have been in equilibrium. Oxygen levels plateaued after the Great Oxidation event, hovering at low but persistent levels. Carbon dioxide concentrations were likely higher than today, helping to keep Earth warm under a fainter young sun. Methane, once a dominant greenhouse gas, declined but did not disappear entirely. This balance of gases prevented either extreme greenhouse conditions, like Venus, or runaway cooling, like snowball Earth. It was a finely tuned equilibrium that lasted for hundreds of millions of years. The stability of Earth's climate may help explain the slow pace of evolution during the boring billion. Environmental stress, such as ice ages, volcanic events, or asteroid impacts, often drives rapid adaptation and diversification. By contrast, a stable world places fewer pressures on life. Microbes had little incentive to change. Stromatolites thrived undisturbed, microbial mats covered shorelines, and eukaryotes persisted in small populations. Evolution continued, but at a leisurely pace. Without the accelerants of disruption, stability in this sense was both a blessing and a break. Despite its reputation, the boring billion was not completely uneventful. Geological evidence suggests small fluctuations in carbon dioxide levels, minor climate oscillations, and gradual changes in ocean chemistry. But compared to later upheavals, these shifts were modest. The most important long-term trend was the slow buildup of oxygen in surface environments. While not enough to transform the biosphere, this gradual rise set the stage for future leaps in complexity. The calm of the boring billion was therefore not static. It was preparation. Earth's billion-year climate stability offers insights into planetary habitability. For a world to host life, extremes are dangerous. Too much instability and ecosystems collapse. Too little change and evolution stagnates. The boring billion shows us the power of long-term balance, a world where conditions held steady for nearly 1 billion years, allowing life to persist and experiment quietly. For exoplanet research, this raises important questions. Could a stable planet elsewhere in the galaxy sustain life for billions of years? Could it give rise to complexity, or would it stall, as Earth did during the boring billion? The answers may determine how we search for life beyond our world. As you drift into sleep, imagine Earth 2 billion years ago. The skies are hazy but calm, the seas warm and shallow, the continents gathered into vast supercontinents. The air is steady, the climate gentle, the world unchanging across countless generations. For microbes, this is paradise, predictable, secure, abundant. Picture the quiet rhythm of waves against stromatolite reefs, the steady bubbling of oxygen into shallow waters, the endless repetition of days and nights. It is a world without drama, but rich in endurance. A world holding its breath, waiting for the next great transformation. When astronomers search the skies for planets beyond our solar system, their goal is not just to find rocks orbiting stars, but to find places where life might exist. One of the most important lessons from Earth's own history, especially from the boring billion, is that life and habitability are not simply about having water. They depend on balance, stability, and time. Earth's billion-year stretch of climate stability offers a valuable window into what might make other planets habitable and how life elsewhere could evolve. The boring billion reminds us that life requires patience. On Earth, it took over 2 billion years from the planet's formation before complex multicellular organisms appeared. Much of that time was spent in relative calm, with few dramatic environmental changes. If another planet hosts oceans and an atmosphere, we should not expect life to spring instantly into complexity. Instead, it may linger in microbial form for billions of years, just as it did here. This has a direct impact on exoplanet studies. When we detect a potentially habitable world in the Goldilocks zone, we must remember, even if liquid water exists, the planet may be locked in its own version of the boring billion. Life could be present but invisible, simple microbes thriving quietly, without yet making dramatic changes to their world. One of the great challenges in astronomy is finding biosignatures, chemical signals that indicate the presence of life. On Earth, oxygen is a key biosignature, produced in massive quantities by photosynthesis. But during the boring billion, oxygen was present only in modest amounts, not enough to dominate the atmosphere. If we looked at Earth during this time from light years away, we might not immediately recognize it as a living planet. The biosphere was active, but its signatures were subtle. This teaches us caution. When studying exoplanets, we must be prepared to find worlds that harbor life without showing obvious chemical clues. Astronomers now consider false negatives, as well as false positives. A false negative occurs when life is present but undetectable, as Earth would have appeared during the boring billion. A false positive occurs when chemistry mimics life's signals without biology being present. The boring billion shows us that both are possible, reminding us to look deeper than surface impressions. The arrangement of continents and oceans played a major role in stabilizing Earth's climate during the boring billion. On distant worlds, we cannot yet see continents directly, but their presence would affect climate patterns, ocean circulation, and atmospheric chemistry. A planet covered entirely by ocean, for example, might avoid some extremes but also lack the weathering cycles that help regulate carbon dioxide. By contrast, a planet with large supercontinents could experience long periods of stability, as Earth did. If we detect exoplanets with unusual stability in their atmospheres, it may hint at a similar geologic arrangement beneath. Many exoplanet studies focus on whether a planet is in the right location to support liquid water. But the boring billion reminds